Emerging Trends in Photonics 2024 1 week offline faculty development program sponsored by ATAL Academy. Welcome you all. In the second expert session, we have Professor from IIT BHU. I welcome Dr. Omji Pandey sir. A brief introduction about Dr. Omji Pandey sir. Dr. Omji Pandey sir is currently working as assistant professor in Department of Electronics Engineering, IIT BHU, Varanasi. Prior to joining IIT BHU, he was working as an assistant professor in Department of Electronics and Communication Engineering, School of Engineering and Applied Sciences, SRM University, Andhra Pradesh. He worked as postdoctoral research fellow with the Department of Electrical and Computer Engineering, University of Saskatchewan, Canada, under the guidance of Professor Ha H. Nagyun. After completion of his PhD program, he has worked as a research fellow with Professor Rajesh M. Hegde in Wireless Sensor Network Lab at IIT Kanpur during 2019. He has also worked with industries. As a part of educational qualification, he has completed his PhD degree in January 2019 from the Department of Electrical Engineering, IIT Kanpur. He received his MTech degree in Digital Communication from ABV IIT Gwalior in 2013. He obtained his bachelor degree in Electronics and Communication Engineering from AKTU in 2008. His research interest lies in signal processing, communications and communication of wireless network, with a specific focus on robust sensor node localization and tracking over wireless ad hoc network. He has also worked on related areas just like as a network, lifetime maximization, energy harvesting, network robustness, low latency and energy balance data transmission, time synchronization, data fusion, data aggregation, and many other fields. He has also worked on blockchain enabled IoT, physical layer wireless network. He has published more than 50 research articles in SCI Index journals and has been the part of various reputed conferences. He is senior member of IEEE IET fellow. He is regular reviewer of various reputed journals including IEEE transaction for on green communication and networking, IEEE transaction on network and service management, IEEE transaction on network science and engineering, IEEE transaction on wireless communication, IEEE transaction on communication, IEEE transaction on vehicular technology, IEEE system journal, IEEE sensor journal, IEEE Internet of Things, IEEE SS, and many other reputed journals. Sir is also serving as associate editor of IEEE transaction on network and service management, and which have impact factor of 5.3. We are really very pleased with person with such kind of the versatile experience is with us. I welcome him at the campus of Rajki Engineering College Sonbhadra, and definitely sir, your lecture will be benefited, will definitely benefit our whole department in various aspects. Thank you very much, sir.
Thank you very much, Prasanji, for giving such a brief introduction about myself, and I'm thankful to Dr. Tripathi as well for providing me an opportunity to deliver a talk in front of you all. So the title of the presentation I have kept two presentations. One is on UAB assisted optical wireless communication solutions for Internet of Things. So first we should understand that what exactly this talk is. So we are basically talking here about the Internet of Things, that how the networking will happen in the Internet of Things, and essentially we are talking about unmanned aerial vehicle assisted optical wireless communication solutions, because like if you are aware about 5G and beyond wireless communication, then you are aware that we are doing this backhaul infrastructure development. So that is majorly focused with be on optical communications. So what I am going to talk to in front of you all, that is how the routing mechanism will take place within the Internet of Things. And first I'll just give a brief introduction about optical wireless communication solutions, and then we will move into the a new terminology, that is a small word phenomena in the context of Internet of Things, that how routing mechanism will happen. So optical wireless communication, I think most of you will be familiar that what is this optical wireless communications, and we are talking about infrared and visible light and ultraviolet communications, and I think majority of you will be aware that what will be the frequency range over which it will work. So we have highlighted with the different colors that this optical wireless communications. Now if we want to understand that what is the fundamentals behind optical wireless communications, then we are having, even if you are talking about digital communications also, then you are having transmitter and receiver, and within that you will do several kind of things like encoding, source encoding, channel encoding, and various mechanism also will take place. So on similar lines, in the context of optical wireless communications also, we are having transmitter and we are having receiver, and we are having certain constraints, and that has been highlighted as amplitude constraints. So transmitter means you are talking about first baseband processing in electrical domain, and then you are going for this electrical to optical conversion, and where essentially you can use LED or you can use laser depending on the field of view. And then we are having a certain constraint, that is eye safety regulations for lasers and non-negativity of the signal in the amplitude constraints, and as part of receiver we are having optical to electrical conversion, that is going to be used as a photo detector, and then we will do the baseband processing. So this is the whole architecture about optical wireless communication basics. Now if we are talking about optical wireless communications, then what are the advantages, why we are going behind this optical wireless communications? Then advantages are, we are having a large bandwidth capacity, we are having unregulated spectrum, and we are having high degree of spatial confinement, and additionally we are having robustness, and that is very important for any of the network. So that is certain advantages with optical wireless communications. And the use cases, there are plenty of use cases of optical wireless communications, and essentially over which I am working, that is in the context of Internet of Things. So you can also think that optical backhaul infrastructure development, I have already told you, that is also can be developed with the help of optical wireless communications, and there are several other applications also in front of you. Even during my research work, I have also done I have addressed the problem of localization using visible light communications, and that paper is already published in the year 2018. And so these are the plenty use cases of optical wireless communications. So the primary requirement, the main requirement, what we are looking for when we are going to develop a particular network, the main goal will be like high speed. We are always looking for as like ultra fast data transfer. We are looking for mobility and adoption to the channel, robustness, low latency, and precise positioning. So these are the, when you are going to develop not only optical wireless communication, when you are going to develop any kind of network infrastructure, you are looking for these challenges, that how I can address. Even like if you can think that the primary goal of 5G or 6G wireless communication is ultra reliable low latency communication. So these are the primary challenges faced by the researchers in the domain of communications. So those are highlighted in front of you. Now the research scope, if even you can think about ultra short range or short range or medium range or long range or ultra long range, everywhere this optical wireless communication is going to help you, and there are various applications that belongs to it, like optical circuit interconnects, wide like wireless personal area network, wireless body area network, wireless local area network, vehicular ad hoc network. These are the applications. So in like in various applications we can use this optical wireless communications. Now, what are the working goals when you are going to design a optical wireless communication model? Then in which areas you will look to address the challenges? So challenges are propagation modeling and channel characterization, that is one domain, or you can say it is a like a broad area over which people are working when they are looking for optical wireless communication solutions. Physical layer algorithm design and verification, and networking protocols and advanced photonic components, and essentially I am working on networking protocols. So if you will ask me that my research area, so I am working on the networking, and essentially I am trying to develop some of the intelligent routing mechanism within the wireless network to address the challenges. So the same thing what I have shown you in the previous slide in more detailed way, it is given over here, and you can see that networking protocols means that you are going to design an analysis of upper layer protocol stacks and investigation of coexistence and interoperability of optical wireless communication with other communication networks. So that is the networking aspects. Now I just want to move to this one, like I just want to go to the next another presentation. So how like we can you ask? I think no, these are the slides. I want to open that second presentation. Right, so this one will be in the presentation mode. I have to keep this one. How you will keep this one into presentation mode? No, presentation mode, this one. Full. So I feel that you are able to understand that we are going to use this optical wireless communication when we are going to communicate between two devices. Now I told you that we are essentially focused with the routing mechanism. Now routing mechanism, when you will look into the network, I think you are aware about various routing mechanism like Dijkstra's shortest path routing algorithm or Floyd mechanism, or various other algorithms are there. But what exactly we are doing, we are developing, we are introducing a new method, that is small word models for IoT applications. So right now you can just understand that how the data between over the network, how the data will be transferred from one device to another device. So suppose we are looking for two randomly selected devices, and we are finding that there are large number of hops are going to lie between these two devices. Then we are trying to minimize the number of hops required to transfer the data. So this small word phenomena we are going to introduce in an IoT network, and we are going to improve the performance of the network in various contexts. Either it is energy efficiency or latency or data throughput, or you can say residual energy or energy balancing phenomena. So right now from this presentation you just understand that we are having an IoT network. As I told you that IoT applications, we are having an IoT network, and within IoT network we are trying to introduce a small word phenomena. Now what is a small word phenomena? Before understanding this, we should understand that what is cyber physical system and Internet of Things. So you can see from the left bottom that is wireless sensor network. Wireless sensor network, you can see that there are various several number of sensors. They are deployed and they are monitoring the area of interest over a limited radio range, and the data is going to be transferred to the sync node, which is connected to the internet, and through internet the end user is connected and it is getting the information. It is getting the what is the actual scenario, what is the actual conditions of the area of interest. So, due to limited radio range, it is advantageous to us, because like you are not transferring directly data over a long distance. So, if you will talk about wireless sensor network, then it is going to use IEEE 802.15.4, that is Zigbee protocol, and we are transferring the data in a cooperative manner. So, this is all about wireless sensor network. Now, you can build this wireless sensor network with the help of optical communications also. You can use any kind of communications, you can use LoRa communication also, you can use Wi-Fi also, you can use Bluetooth also. Ultimately, we are looking for transferring the data from one sensor node to another sensor node, and it will be in a cooperative manner, and ultimately the data will be fetched by the end user, whatever the data has been monitored by the sensor nodes. And a real field sensor node deployment is shown to you at the right bottom, that is that how in real field the sensor node has been deployed. And the middle part of the figure is showing you that what is the cyber physical systems and internet of things. You can understand that this whole physical world is sensing the physical world phenomena, and it is transferring the data to the cyber world, and at the cyber world various computations will be performed, and the cyber world will try to understand to get the inference of the about the what is the actual situation of the physical world, and it will generate an actuating signal to control the physical world phenomena.
So, in cyber world, processing is in edge computing or computing?
So, it is depending on that what kind of infrastructure we have developed. For example, you were talking about edge computing and fog computing, then it is basically when you are looking for very fast response from the system. So, what we are basically going to do, we are going to assign certain number of devices to a particular edge server, and that will be responsible to respond only certain number of IoT devices. So, what we are basically doing with the help of edge computing, we are bringing the server closer to the devices, so that we can get the faster response from the server. So, that is edge computing. And if you are having a robust system, you are having a secured system, then you will say that this cloud is also fine with me. So, depending on that what kind of infrastructure you are developing for your network, it might be cloud, it might be fog, it might be edge also, that what kind of network you have deployed. So, as we have understood that wireless sensor network is going to work as a backbone for cyber physical systems and internet of things. So, you can see this is the wireless sensor network architecture. It is consisting of 3 layers. One is bottom layer, that is hardware layer, one is middleware layer, and at the top we are having application layer. The middleware layer used to communicate with the hardware layer using operating system and communication protocols, and middleware layer used to communicate with the application layer with using application abstraction module. Essentially, what I have worked during my PhD and after PhD, I have addressed the problem of node localization, time synchronization, low latency and energy balance data transmission and data aggregation, which are highlighted within the WSN service module. And there are other issues over which currently I am working, but I have not got any significant results in those contexts. But yes, like resource management and cross layer optimization, security and coverage, these are falling within this WSN service module. So, this is the wireless sensor network architecture. Okay, so what we understood so far? We understood that optical wireless communication is we are using a unguided wave to transfer the data between pair of devices. Now, what I have told to you that it can be optical wireless communication, it can be any kind of wireless communication medium you can use. And after that, what is our goal? Our goal is to address the issues of Internet of Things, IoT network. Now we have understood also that what is cyber physical systems, Internet of Things, and wireless sensor network. Okay. Now I have told you that wireless sensor network is going to work as a backbone for cyber physical system and Internet of Things. That's what I was thinking, that I should show you that what is the architecture of a wireless sensor network. Okay. Now if I am talking about CPS and IoT driven smart world, then you can see that there are various applications of IoT. For example, you are talking about smart homes, healthcare, smart cities, retail, connected cars, and plenty of applications are there of with the help of CPS and IoT, which are making the world smarter and smarter.
CPS means
Cyber physical systems. So like there is a confusion that what is the difference between wireless sensor network, IoT, and CPS, because these terminologies are very frequently used by the researchers. So because you asked, so CPS is basically when we are going to integrate the actuation along with Internet of Things, along with sensing you are going to incorporate the actuation, then that phenomena is going to be known as, that whole system will be going to be known as cyber physical system. Actuator is also there. Okay, so that is IoT or wireless sensor network, you can say. So these are the CPS IoT driven smart world. Now because we have understood now that what is a wireless sensor network, what is Internet of Things, what is cyber physical systems, what kind of medium we are going to use to communicate between two devices. Now as I told you that this presentation is about small world models for IoT applications. So we should understand that what is the meaning of a small world. So this is the person Stanley Milgram who observed this small world phenomena in the year 1967 by performing certain mail delivery kind of experiment in the social context. And what he has done, like he selected a large set of people and randomly selected 2 persons and tried to transfer the mail from one person to another person. And what was his observation? He observed that if you are choosing 2 random persons in this world, then they are not more than 5 to 6 steps to each other. Any 2 persons in this world, they are connected by 5 to 6 people. In 5 to 6 steps you will be able to transfer the information. For example, suppose somebody is in Japan, you want to transfer, then you will identify that in nearby places who is living in Japan. If you are able to successfully identify that person, you will give your information to him. And when somebody is in Japan, he will try to understand which city within the city. Like in this way he performed this experiment and he concluded in this world 2 randomly selected persons are not more than 6 steps to each other. That is very interesting, and this experiment was performed in the year 1967 by Stanley Milgram. Okay. Later in the year 1998, there were 2 persons, Duncan Watts and Steven Stogate. They observed the same phenomena within the graph. What they have done? They took a regular graph, that is illustrated at leftmost. Regular graph means well structured, well organized graph. And what they did, they performed certain rewiring within the graph. Now when you are going to do the rewiring can be with large extent, rewiring you can do with less extent. So when I am talking about extent, then I am telling that what is the probability of rewiring, that how many links you are doing rewiring within the graph. So when we are choosing a very small probability of rewiring, we are getting a small word graph, and when we are going to increase this probability of rewiring, then we are getting a random graph. Okay. So what is the advantage? Why we are looking for a small word only? Why we are not looking for regular graph? Why we are not looking for random graph? So the advantage is, suppose you are having a regular graph and you have to transfer the data. Suppose you have to transfer the data from one node to another node. Now you will observe that many hops are required when you are transferring the data between two randomly selected nodes, because the long range links are not existing within the graph, right. So the disadvantage with a regular graph is it is having high average path length. Average path length, I am telling that how many number of hops are required to transfer the data between two randomly selected nodes. Now when I am moving to a small word, you can see that we have created three long range links, we have rewired them, and with the help of this long range links we are able to transfer the data with very less number of hops, which was earlier 10 hops or 11 hops. Now we are able to transfer in within 2 to 3 hops, that is reducing the average path length. Now the third graph is random graph. Now you can see that random graph is even more faster. You are able to transfer the data in a very fast mode, because there are large number of long range link existing within the random graph. But the disadvantage is, like, they are isolated. If any node is dead, then he is out of the network, out of the graph. Means what I just want to tell you from this particular figure, I just want to tell you that we are looking for low average path length and high average clustering coefficient. Low average path length and high average clustering coefficient means we are trying to transfer the data with minimum number of hops, and we want high average clustering coefficient. High average clustering coefficient is telling you that suppose in the network some node is in trouble, means some node is having less residual energy, then he can transfer its data to closer node, and he will be the responsible person to transfer the data to the sink node. So we are looking for, these are the two properties, average path length and average clustering coefficient, and they are going to define the small wordness within the graph. I hope you are able to understand. Are you getting or not? So this is the two properties, and they are also illustrated in this particular graph. This regular graph, small word graph and random graph, we have plotted with varying rewiring probability, and we are showing that this small word region is the region in which we are having low average path length and high average clustering coefficient. In case of regular graph, you are having high average path length and high average clustering coefficient. In case of random graph, you are having low average path length and low average clustering coefficient. So I think that I am able to successfully convey you that why we are looking for high average clustering coefficient and low average path length. If suppose I am talking in terms of wireless sensor network, if I am talking, what I told you, that what is the definition of wireless sensor network? The definition of wireless sensor network, simple, that we are monitoring a particular area of interest, we are deploying plenty of sensor nodes. There is a difference between sensor and sensor node, right? I believe that you are able to understand that what is the difference. Sensor is just an entity which will sense the physical world phenomena, temperature, pressure, humidity or other. But sensor node is consisting of transceiver unit, processor unit, sensing unit, various units with it. So what basically sensor node will do? Sensor node will sense the phenomena and will perform certain operations on it, and ultimately it will transfer the data to the next node. Now I told you that it will be in a cooperative manner. Why it will be in a cooperative manner? Because you want to extend the lifetime of a wireless sensor network, and for that you want to transfer the data over the shorter distances. So now if you are going to transfer the data over shorter distances, you have to follow the cooperative mechanism. Cooperative mechanism means one node will transfer to another, another node will transfer to another, and this process will be repeated till the information is not reached to the gateway or sync node. So now you can think that suppose you are going to deploy a wireless sensor network where the gateway is connected to only 3 sensor nodes. Now you are having, suppose in the network you are having 400 sensor nodes, but the gateway is actually connected to the sensor node which are 3 sensor nodes which are close to it. Now you are frequently you are observing this physical world phenomena, and again you are transferring the data to the sync node. Now you can realize that that there will be a imbalance in energy consumption over the network, because what will happen, some of the sensor nodes they are sitting idle, they are, suppose they are sensing the physical world phenomena after 1 minute. So what you will realize is that the within the network the residual energy of the network is quite high, but the sensor network is collapsed, because those 3 sensor nodes which are falling closer to the gateway, they will be responsible to transfer the data of all the 400 sensor nodes again and again, and they will die out in the network. So what I have observed that the network is consisting of 86% or 87% of the residual energy, but it is dead because those 3 sensor nodes are dead. So that is the motivation, behind introducing this small word characteristics. So like if at one place I was giving a talk, so one person asked me that if you are able to successfully reduce the average path length, then what is the meaning of maintaining high average clustering coefficient? That is what I am explaining, to let you understand that a small word characteristics is important, not average path length. Okay. So average path length of course is helping us to minimize the number of hops required to transfer the data, but simultaneously we also want to maintain a high average clustering coefficient over the network, so that the problem of energy imbalance phenomena can be addressed over the network.
Sir, it may be possible that average path length is less, but still path loss is more.
Path loss actually when you are talking,
always depend on the path length. Suppose path loss coefficient increases.
no, so what you are talking about path loss, when we are talking about path loss, then we used to talk about 2 devices, communication between 2 devices, and when I am talking about path length, then I am talking about the entire path routing. What you are talking, that is communication, what I am telling, that is networking. Okay. So path loss means like log normal path shadowing model, what you are telling, that is like attenuated by like in an exponential manner. As the distance will increase, the received signal strength will decrease in an exponential manner. Means we want to transfer the data very to the closer device, but that is between 2 devices. What we are talking about 2 devices. What I am talking average path length, I am talking about the like 2 randomly selected devices, and we have to successfully transfer the data between those 2. So you have to follow a path, that which path I should choose so that the network performance will be improved. I can use shortest mechanism, Dijkstra's shortest path routing mechanism, I can use any mechanism. So what exactly I have done, by observing that if you are able to successfully incorporate this small word characteristics within the network, then you are able to improve the network performance, what we have observed. Okay. So these 2 properties, average path length and average clustering coefficient, both are important, and we are looking, we are like both things we are claiming as this is a small word characteristics.
Sir, energy harvesting concept cannot be applied in a sensor network. So some nodes which are more prone to die, we can harvest by the
Yeah. It is like, it is a very good problem. I'm also like, I was exploring 2-3 years back. Since 2-3 years I'm exploring this one. But what I have observed, that you can use this concept of energy harvesting at those places where you are having significant amount of energy somewhere and you are getting charged up. For example, in the context of unmanned aerial vehicle, this is fine. But if you are talking about wireless sensor network where from external places you cannot supply the power, then I think energy harvesting is useless. Because what will happen, that we are somewhere we are wasting 50 watt to get charged to get 1 watt. Like, we are giving 50 watt energy and ultimately we are getting 1 watt. Energy harvesting means, like, you are talking about energy harvesting in RF context, radio frequency. If you are talking about radio frequency, you will realize that when you are transferring, what I have done the experiment, I have observed, I was also very much motivated to work on this energy harvesting, but when I did simulations, because like you have to what the path loss model you have told, you have to observe the diffraction, refraction, reflection, all those mechanism will take place between two devices, and ultimately what I have observed, that I am wasting a lot of energy and ultimately I am getting very small energy. Then I was thinking that what like
Sensor, it is difficult to recharge that sensor.
then it is like application oriented. Then you can say that somewhere from UAV is getting charged up, it is coming to close to that sensor node and it is giving like it is recharging to that particular sensor node, then it is fine. But if you are telling that I don't have external energy, I have to charge through RF energy harvesting I have to do, then it is useless. What I have observed, in my opinion. But recently I have seen many research articles who are doing this RF energy harvesting, but they are specific application oriented.
So that only specific application oriented papers are not selected.
No, they are selected, and of course they should get selected. Why? Because they are very specific to a particular problem. For example, suppose you are talking about a rescue operation. So one person is suppose dying for something, and with the help of UAV you are charging him. So for now, at that particular case, if you are even wasting 500 watt to get 1 watt, that is useful. So that is application oriented, means like that is depending on the demand, that is depending on the need. So at that time you can do. But in general, if you are talking about in normal networks where that is not a critical or application, then it is useless. So this small world wireless sensor network, one illustration, this is this was one student, Gaurav Sharma. In the year he started on a small world mechanism in 2005 itself, and what he did, he basically introduced wired links within the network, long range wired links. You can see that blue dots are indicating the sensor nodes and red dot, big one, is indicating the sync node, and yellow rectangles are indicating the transceivers, and between two transceiver he applies this wired links, and he created this small world phenomena. So this is just an illustration, because like when I was doing my PhD, I got this paper and I was very much motivated from this paper. So that's what, like, I have taken this particular image from that particular paper. So this is the small world wireless sensor network developed by me. The first row is indicating the simulated IoT test bed, you can say, and the second row is indicating the real field IoT test bed. The first column is indicating the conventional IoT network, and the second column is indicating the small world IoT network.
All simulation are done in MATLAB.
No, the simulation what I have done, that is on the MATLAB, but the real field sensor node deployment what we have done, that is we have used NI sensor modes. NI 3230 we have deployed over a residential area in IIT Kanpur, and we have used this Kubuku robots to transfer the data between two node pairs. So, what exactly we are doing from this diagram, you should understand that what exactly this diagram, those blue dots are indicating the sensor nodes, and this 400 cross 400 area I have taken. There are total 300 sensor nodes deployed within the network in the simulated scenario, and in case of real field sensor node deployment, I have taken a area of 33 meter cross 29 meter, and I have deployed 80 NI sensor modes, and that is the conventional wireless sensor network. And a small word, we have used Kubuku robots, and those robots, now the critical part is that how to identify that at which place I should place the robots, so that I will be able to optimize the network performance. How many robots I should deploy over the network, so that I can optimize the network. How you will do the path planning, so that you can avoid the collision avoidance, so that you can avoid the collision. So, there are various questions, but what basically we have done, the paper is published in IEEE Transactions on Vehicular Technology. The title was Joint Localization and Data Gathering over a Small World Wireless Sensor Network with Optimal Data Mule Allocation. So, we are jointly localizing the sensor node, and we are doing data gathering, like we are getting the maximum throughput over the network, and that is going to be done with the help of optimal data mule allocation. We are optimizing the small world characteristics within the network, and we are doing we are allocating optimal number of data mules over the network. So, this is the concept. I hope that it is clear, right?
So, how you program the
Lab view. You will observe all those things on lab view. So, this is the deployment. Now, what is the motivation? Because like I have worked on a small world wireless sensor network, so how I was motivated. So, when I started the my journey in this direction, then these list of papers, not only this is a limited number of list of papers, but there are other papers are also through which I was very much motivated, because like I observed that when if you are able to successfully introduce this small word mechanism, you are able to reduce the localization error, you are improving the data latency, you are improving the time synchronization, you are improving the you are making the uniform energy consumption over the network. So, these were the papers which were working as a motivation for me to work on this particular problem. And what I observed, that what the methodology they are using, that is not very effective. I can improve the performance, like these not a single paper is using this machine learning technique to introduce this small word characteristics. And if you are able to introduce this if you are able to introduce this small word characteristics using machine learning, then you will be better in a better position, you will get better performance. So, that was kind of motivation. In the earlier stage, I was also not following this machine learning, but currently I am working on machine learning techniques. Even you can explore my research profile, you will find some of the machine learning techniques I have proposed to introduce this small word characteristics in IoT networks. So, these research papers were working as a motivation for me to work on these small word models. Now, what are the existing methods? So, I have shown you one research work by Gaurav Sharma, where he introduced this small word using wired links. There are several other methods, like apart from this wired links. The primary challenge is, like if you will say somebody that I am working in the area of wireless sensor network, and you will tell to him that I am going to introduce this long range links using wired connection, he will laugh at you. Okay. So, this because like and forget about this making the fun of someone, you will realize that these things are not applicable at various applications. For example, battlefield surveillance or flood monitoring you are telling, and you are going to introduce the long range links using wired connections, that is not applicable. So, that is the that you can say that it is not feasible solution. Second one is introduction of heterogeneous sensor node. Heterogeneous sensor node means like you are having the sensor node which are having different radio range transmission capability. Like you can, with the help of software defined, you can activate the sensor node with a shorter radio range transmission, with higher radio range transmission. You can reduce that radio transmission range. So that is known as a heterogeneous sensor nodes. Regarding battery power means like you will use the same power will be same, only with the help of software defined you will execute that which radio is going to be activated. It will be like if you are going to transfer over a long distance, obviously you are going to consume the power of the device, like because the if you will see this power consumption of a device will depend on the distance. It is d square and d power 4. There are two power ratios over which a device will consume the power, depending on that it is transmitting the data below a certain threshold or above that particular threshold. So obviously if you are going to increase the transmission range, the device will consume more power. No, in transmission power will be consumed. And also again it is depending on that you are processing huge amount of data or what kind of data you are processing. Sometimes computation it's itself very like energy consuming process, but majority of research papers you will observe that in the transmission the power consumption will be more. Even people used to tell that 80 to 90% of the energy of a device will be consumed when it is transferring the data, not processing the data.
Suppose we done some algorithm in MATLAB, this laptop, our battery drain very soon.
Now you can realize that if you are in your mobile phone, if you are using the internet of the service provider like Jio or Airtel, if you are activating that one, the battery discharge will not be up to that level. If you are enabling Wi-Fi, then it will whatever, like suppose you are connecting your mobile phone with some router and you are activating Wi-Fi, then the power consumption will be drastically there over the mobile device. And that is the reason, like when we are developing a wireless sensor network, we are basically using IEEE 802.15.4 Zigbee protocol. Zigbee protocol, if you are talking, then it is having a data rate of 250 kbps maximum, but when you are talking about Wi-Fi, it will beyond 1 Mbps, and that is the reason the battery discharge will increase because you are activating Wi-Fi on your mobile phone. And that is the primary reason that wireless sensor network, if you will ask someone that I am going to deploy a wireless sensor network, he will tell you that you are going to use this Zigbee protocol. Always there are many things, like a wireless sensor network is based on SMAC protocol, that is based on the Zigbee protocol. We are having the TCP UDP, if you are talking about, then it is not applicable in wireless sensor network. You have to use a different mechanism for the MAC. So there are many things, like ultimately you can just understand that in life, if you are losing something, then we are gaining something, and if you are gaining something, then we are losing something. For example, they are listening to me, they are not able to play cricket. Okay, so like if you are able to increase the data rate, then simultaneously you are consuming more power. So to optimize the things over the network, depending on the applications, for example, you are going to monitor a unattended area, then you have to run the batteries for the years, and if you want to run the battery for the years, you have to come up with certain protocols which will be having less data rate, so that the devices will consume less energy. Okay. So all these things are depending, they are application oriented, they are like I believe that you are able to understand that depending on your application, that you are looking, as you told in the beginning itself, that you are talking about edge computing or fog computing or cloud computing. So edge computing is having its own advantage, cloud computing is having its own advantage. For example, like if fog computing is like, you can say this is a moderate level of cloud and edge. It's like when you are bringing very close the servers very close to the devices, then it is edge computing. When you are keeping at moderate level, then it is fog computing, and when we are keeping far away, then it is cloud computing. Okay. So they are having own advantage and disadvantage. For example, if you are talking about this edge computing, then your system will be less secured, because you are giving the flexibility to many servers. Any servers will be attacked, and the system, he can get the information of the system. But in the cloud computing, hackers have to hack this cloud, and because of this security purpose, right now I think you have heard this federated learning and blockchain technology, because they are distributed technologies. So they are making the system more secure for edge computing, because what is happening in edge computing, you are sensing the data and raw data will be transmitted to the cloud. Now you want to cloud not to receive the data, you are using federated mechanism, federated learning mechanism, where the trained model parameters will be only sent to the cloud rather than sending the data. But again, federated learning system is again facing some challenges. What are the challenges? Still you are focusing on this a single server, and if that server is collapsed, the whole system is collapsed. So you are incorporating, recently one of my research article is published in IEEE Transactions on Circuits and Systems brief, where I have incorporated this federated learning and blockchain technology in IoT network. Okay. So there are many things. Okay. So these are the some of the research work published by me, and after these are the till I think year 2020. After that also I have published many research papers, but they are like initially I have worked on these research papers. I have addressed the problem of node localization, data gathering, low latency data transfer, energy balancing, and fault resilient distributed detection and estimation. Wireless ad hoc network, you can say that is infrastructureless. Ad hoc network is without infrastructure, means any point can work as a server, and at any time you can change, like infrastructureless. Wireless sensor network, if you are talking, you can make wireless sensor network also ad hoc network. But what usually people used to think about wireless sensor network, that you are having a specific sensor nodes, you are having a sync node, and the data is going to be transferred to the sync node, and sync node is connected to internet, and internet is connected to the end user, and finally from the sync node the end user is getting information. So kind of you can say wireless sensor network is a with infrastructure it is there, but you can make wireless sensor network, you can make ad hoc as well, there is no issue. You have to just convert, you have to just make it infrastructureless, means at any time any device can also work as a server. If you are able to provide such kind of flexibility, then you can say wireless sensor network is also a wireless ad hoc network.
If we talk about the availability of power, so wireless ad hoc network will have a
more flexibility in wireless sensor. The primary challenge with wireless sensor network is power. That is what, like, if you will read some of the papers on wireless sensor network, you will realize that many researchers are addressing the problem of energy in the wireless sensor network, that how I can minimize this energy consumption over the network. But if you are ad hoc network, if you are talking, then you have to make individual device also server sometimes, so that they can process the data, and that capability is not available with the sensor nodes if you will do that. But if you are able to provide, like, wireless sensor network is what? Wireless sensor network is just the devices are sensing the phenomena and they are transferring the information with low data rate. And why with low data rate? You can increase the data rate also, no problem. Then you have to replace this Zigbee protocol with some other protocol. So that, for example, like now you can see that LP WAN technology is coming, low power wide area network. where the devices are using LoRa communication protocol. LoRa communication protocol is using CSS modulation technique, chirp spread spectrum modulation technique, and that is helping you to transfer the data over the longer distance with minimum power. Means if you will plot the power consumption with distance, then you will observe that after certain distance the power is getting saturated. Means even if you are transmitting the data 3 km or you are transmitting directly data 6 km, the power consumption will be same. So you can use LoRa communication also in wireless sensor network. You can use I told you na that if you are having the flexibility, like also now why basically TCP is going to be used in emails, why UDP is going to be used in live broadcasting, depending on, suppose your information is very important, suppose your like if you are writing an email, that is very important, right? So you don't want to lose any information, so that is basically using TCP protocol. But when Virat Kohli is doing batting, Virat Kohli, like if he is, like if you are able to miss some content, that how he played the shot, that is not a matter of big deal, like ultimately it is 4 or 6 or he is bowled, that is the important thing. So ultimately if you are getting some bits of information is lost also, then it is not much, you will not, so that is what you are going to use UDPs. So now it depends on like what kind of, you have developed this ad hoc network for what kind of application, your data is important or not, each and individual bit is important or not, depending on that you will activate this protocols. They will of course consume more power, because like TCP is acknowledgement based, means you have to identify that my packet is received or not. So for that again a transmission will take place, either it is 1 bit flag bit, but you have to retransmit, so of course it will be power consuming, less power. You can use, but UDP further, if you will compare with other protocols, like if you will see the MAC protocols at data link layer of wireless sensor network, then you can see that BMAC, TMAC, SMAC protocols, they are even further more less power consuming protocols in comparison to UDP and TCP. So for specifically for wireless sensor network, these protocols are going to be used. So because like they are you can see that not very much data oriented, not very much data oriented, because like in wireless sensor network also you will realize that data is not going to be generated very frequently. For example, in this room if you are sitting, then wireless sensor network will that will do, that will monitor the temperature of this particular room, and the temperature of the room is not going to change every second. Okay, so that's what like, and that's what you are, when you are developing a wireless sensor network, you are looking for data rate of 250 kbps, because you are not much bothered about that how fast it is transferring the data. Exactly. Duty cycling, many papers you will observe that people are proposing algorithm of duty cycling also in wireless sensor network, that when I should switch off, when I should the sensor node should wake up. So so those things, like you are having the flexibility, of that. One more protocol I heard in sensor network, leech is different. Leech is basically this what SMAC and BMAC and TMAC I told, that they are MAC protocols. Leech protocol is basically for the clustering of the sensor nodes, that how you are doing the clustering. Because why you are doing clustering? Because like yes, because like what you are doing, like I told you na in the beginning, even I will show you some of my results. I have my algorithms what I have proposed, they are doing better than Leech, and my paper is getting cited. I am very happy that is getting good citations. I have improved the performance over the so 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 these are the some of my research contributions what I have made. and one of the research problem, the first research paper what I have written, that is I have introduced this small word phenomena using iterative average path length reduction. So what I am doing, basically this argument minimization of average path length is giving me the how many number of links I should introduce in the network, and between which node pairs I should introduce the link, so that I will be able to introduce optimal small word characteristics within the network. So this is the mathematical formulation what I have done. Right now you can see that in the objective function I have only kept this average path length. I have only kept average path length. I think this expression, by looking this expressions, you are all BTech students. So don't get it. This is very simple. It is just like I'll explain you. It is just like they look horrible, but they are not horrible. Okay. So like see, this is the objective function I have taken. Like in simple language I am explaining that what is happening in this. This is my average path length, and I am trying to, like, I can minimize this one. I can minimize this objective function, and what I am trying to do, I can use some of the parameters. I think you have not gone through convex optimization. You can minimize this function. If you are, after minimizing this particular function, some variables are responsible to minimize that particular objective function, then if you are applying argument minimization of that, then that particular variables will be returned to you, optimal values that will be returned to you. So argument minimization of average path length is returning me the number of links and the set of node pairs between which I should introduce the long range link, so that I will get the small word characteristics. Now you will say that how you are getting a small word? You are minimizing simply this average path length. You are not bringing average clustering coefficient in it. So you can see that in the constraints I have kept average clustering coefficient. I have kept average clustering coefficient in the constraints. So what is happening? What you can understand here from this particular mathematical formulation, that over the network I am introducing long range links, certain long range links I am introducing. What is happening? When I have introduced first long range links, I observed that my average path length reduced drastically, while my average clustering coefficient is reducing with very less value. I want low average path length and high average clustering coefficient. What happened? Like first link I have introduced, then second link I have introduced, then third link I have introduced, but after certain number of introduction, I realized that my average clustering coefficient reduction is more in comparison to average path length reduction. Then at that particular point I am stopping to introduce the long range links. Okay, are you able to get? उसमें कोई घबराने की बात नहीं है कि ये बहुत ऐसा मैथमेटिकली लिख दिया, कुछ बहुत सिंपल है ये. एक्चुअली जब आप बैठे होंगे ना, इस पेपर को अभी मेरे पढ़ेंगे, बहुत सिंपल है ये. ओके, बस ये आप समझिए, लाइक यू कैन नॉट कंपेयर किलोमीटर विथ kg, right? So for that sake I have done the normalization. I am normalizing, like clustering coefficient divided by clustering coefficient will give you unit less quantity. Average path length ratio by average path length will give you a unit less quantity. Now you are having two unit less quantities and you are comparing them. Then it is valid. So that's what I have divided everywhere. And what I am looking for? I am looking for that at a particular instant the reduction in average path length is more or reduction in average clustering coefficient is more. If reduction in average clustering coefficient is more, at that particular point I will stop introducing the long range links within the network. That is the whole thing. Okay, and that thing I have written mathematically. Now these are the variables what I have used in the previous formulation, so leave it. Now this is an illustration which you can see, you can understand by your own also. What is happening? There are two graphs you can see. In one graph, what I have done, in the same color I have introduced the long range link, and in the next graph I have introduced the links with different colors and I have also given the numbering to them, 1, 2, 3, 4, 5, 6. Okay, what is happening? You can see from that particular graph what I am doing at a particular time instant. I am identifying that which node pair I should select to create long range links, so that I will get a small word characteristics. And in this, what I am doing, I am introducing first a single long range link. When you will introduce a single long range link, the topology of the network will change, the data routing mechanism will change. Now, in the second iteration, when you will do, then you will get the optimal node pair between which you have to introduce the long range link. So, in this way, at each iteration you are getting optimal set of node pair between which long range link need to be created, so that you will get the optimal small word characteristics. While in this case you will not get optimal small word characteristics, but what is the advantage? Certain advantages are there. What is the advantage? Here you are getting optimal small word characteristics, but it will take more time, because again and again over the whole network you will search the optimal node pairs, while this one will not give you the optimal small word characteristics, but in less time you are able to introduce a small word characteristics. You are able to understand? So, this one I have told as non-iterative method of introducing a small word characteristics, and this one is iterative method of introduction of a small word characteristics. Now, if I am going to compare these two, so for doing the analysis, I have used this real field sensor node deployment. I have given the details over already. I have given details to you. This is the performance analysis. So, you can see that iterative and non-iterative, non-iterative APL, iterative APL, non-iterative ACC, iterative ACC. So, you can see that if you are seeing that iterative average path length reduction mechanism is giving you you can say that it is providing you more reduction in average path length in comparison to non-iterative approach. But if you will compare the time complexity, then the time complexity of the iterative approach will be better in comparison to non-iterative. So, this is the performance evaluation over the experimental test bed and simulated test bed and Intel Berkeley lab data set. You can see that there are 6 lines in each and individual graph. One is over the real data, and I am using this model based approach, this Frisk transmission model. If I am going to use, a log normal shadowing model I am going to use for RSS measurement. Then I have done this one on model free and model based, both approaches I have done. For model free, if you want to understand that how I am measuring the distance between two node pairs, I have taken the reference of this particular paper, which is published in the year in ICC conference, that is very prestigious conference, and one is model based. So, I have taken 3 data set, one is real field sensor deployment, one is Intel Lab Berkeley data set, and one is simulated IoT test bed, and corresponding to each I have observed the performance of localization error, power required, bandwidth required, and number of nodes localized. And you will observe that at 2 places we are getting benefits. One is localization error is going improved in all 3 cases, and in case of number of anchors required we are getting better performance. And the drawback is in terms of power required and bandwidth required, because we are going to introduce long range links. I told you that when you are transmitting the data over shorter distances, the power consumption will be less, while because of introduction of long range links, the devices will consume slightly more power. So, the disadvantages are power consumption and bandwidth required. However, we are emphasizing that we are able to successfully reduce the localization error. So, these are the advantages. Now, if you want to understand this in a better way, further better way, then this is the radar chart. What I have shown, like at upside, this conventional wireless sensor network is plotted, and at the bottom row, a small word WSN is shown. Means the first row is corresponding to conventional wireless sensor network, and the second row is corresponding to a small word WSN. Now, you can see that this radar chart is covering less area in case of a small word wireless sensor network in all three cases, either that is simulated data set, either that is Intel Lab Berkeley data set, or real field deployment. So we are getting better performance in case of a small word WSN. Okay. We have taken the parameters as localization error, power consumption, bandwidth required, APL and ACC, all those parameters we have taken, and we are getting better performance in case of a small word WSN. Now this is the Cramer-Rao lower bound analysis. Cramer-Rao lower bound analysis means like when you are doing this localization error analysis. This is also very simple, don't get scared. Cramer-Rao lower bound is also very simple thing. You have to just get the Fisher information matrix. Fisher information, first we should understand that what is the meaning of Cramer-Rao lower bound. Cramer-Rao lower bound is telling to you that I told you that when you are going to introduce this small word characteristics in the network, then your localization error is reducing. Localization error you are reducing means your location accuracy is getting improved. Now Cramer-Rao lower bound is telling to you that that is fine, that you are getting better localization accuracy, but what is the error variance? Error variance means like suppose you have taken 100 trials, you have done 100 trials, 100 simulation conditions you have taken. Like in one simulation condition you are getting localization error 1 meter, in another you are getting 1.5 meter, in another you are getting 1.3 meter. Various cases will come depending on the situations. Now for 100 samples, for 100 scenarios, you will average out and you will say this is the localization error over the network. Now Cramer-Rao lower bound is telling you that in a scenario, what is the error variance, like maximum error, what is the variation of the error, at what extent the error is going to vary. Okay. So this is the Fisher information matrix expression, and when you are going to do it with covariance matrix, then ultimately you will get this Cramer-Rao lower bound over here, and that will give you the Cramer-Rao lower bound analysis. So forget about this right now. You can just see from this particular graph, you can understand in better way. Now you see that that is Cramer-Rao lower bound in case of WSN, this is Cramer-Rao lower bound in SWWSN, that is the Cramer-Rao lower bound difference, and this is the Cramer-Rao lower bound ratio of these two. Okay. Now you can see that in case of Cramer-Rao lower bound analysis, when you are doing on wireless sensor network, the error variance is going to closer to 3, while if you are checking in case of Cramer-Rao lower bound in case of SWWSN, small WSN, then it is closer to 2.5, means error variance is going to reduce. If you are able to successfully reduce the error variance, obviously the localization error will also reduce. So this is a kind of not any new result, this is kind of another way of seeing the same thing. And you can, like, to better visualize, we have taken the difference of these two is always greater, like positive, and the ratio is less than 1 if I am taking the ratio of this with this. So this is the Cramer-Rao lower bound analysis, and this is the next problem what I have addressed. Now this is a new problem. What I have discussed so far, that was on localization. Now this is another problem where I am doing low latency and energy balance data transmission over cognitive small word wireless sensor network, and this is also published in IEEE transactions on vehicular technology. Now what is the objective function? Objective function is Fij n tau is representing the amount of data transmitted between two node pairs, and Cij n tau is representing the cost of the link. And what we are doing, we are looking for all possible transmission over the all possible links over the network. So what ultimately we are trying to do, we are trying to minimize the product of these two. We are trying to minimize the product of these two by minimizing either the amount of data or minimizing the cost over which the data is going to be transmitted. So I hope this is clear to you. What you can understand right now, that you are having a big network. You are having a big network you are having a large number of sensor nodes. Now sensor nodes are transmitting the data. Sensor nodes are transmitting the data. Now in what, over the which links they should transfer the data, and how much amount of data they should transmit on individual link, so that the product of these two will be minimized, means the cost over the network will be minimized. So we have taken the as a constraint, we have taken that if the direct data transmission distance is beyond a certain threshold, then you will not transfer the data on that particular link. That is the first constraint. Second constraint is, on a particular sensor node, the incoming data will be equals to outgoing data, means Fij n tau minus Fj n tau will be equals to 0, means there should be a balance of data flow over the network. And third one is telling that if you are transferring the data on a particular link, means if the amount of data is positive, then the cost corresponding to that link will be also positive. Means if you are transmitting some amount of data, then of course the cost corresponding to that particular link will be also positive. So this is the problem formulation for low latency and energy balance data transmission, and this is the visualization that how I have addressed this particular problem. So sorry.
How we solve this problem? Formulated the problem.
Now I am going to explain that one.
We solve it in MATLAB.
Hmm.
Some
So I am explaining the solutions. Problem is clear? Now I am explaining the solution. Solution is, like you are having black dots, they are the sensor nodes. You are having black links, they are the conventional wireless links. You are having a set of red links, they are long range. Set of blue links, they are also long range link. You can, within this particular graph, you can also visualize green links, magenta links, cyan links, set of links. What I am basically doing, I am taking the 6 properties of the network and node. The properties are hop count distance, clustering coefficient, residual energy, geographical distance, node degree, node betweenness and centrality. Okay. And by looking on these 6 parameters of the network and node, I am assigning a probability to individual node. Okay. Now I will just ask you that if the distance between 2 nodes is shorter than you want to transfer, you will transfer the data, or when it is longer than you want to transfer the data. Like when you are transferring the data, you will choose the shorter distance or longer distance for wireless sensor, shorter distance. So that is the reason I have kept this geographical distance in the denominator, means when I am assigning a probability, I am choosing this geographical distance in the denominator. Hop count distance you want to minimize or you want to maximize. So if the hop count distance is large, then you are assigning the higher probability to it. In similar fashion, all these 6 parameters I have chosen, 3 parameters I have kept in denominator, 3 parameters I have kept in the numerator, and depending on these 6 parameters I am assigning each and individual node a probability. Now when I have assigned a probability to each and individual node, then what is happening? You have to identify, you have to give as an input to your algorithm that you want to create 6, 7, 8, 9, 10 algorithm number of long range links at time instant t1, time instant t2, time instant t3. How many links you want to create within the network? Now what is happening? Suppose why I am telling you that this is going to change, because like once you have suppose at time instant t1 at time instant t1 you have created blue links, suppose. Now when you have successfully created these links and you have transferred the data, this whole property of the network will change, and as the whole property of the network will change, the probability, we should again reassign the probability to individual node, and that is the reason again at time instant t2 another set of long range links will be created. Okay. So you can just I just want to request you that you please refer this my paper, you will understand in a better way. Now this is,
Parameter can we put in optimization toolbox of MATLAB and we can optimize?
you can do, only the thing is when you are doing this, the objective function what you are making, that should be convex. If you are able to successfully make it, then you can use CVX tool and that will give you the optimal parameters. CVX. Okay. So this is the, I just want to show you that I have compared this with my proposed method using leech protocol, conventional network, direct data transmission, and my own method, and successfully I got very good results. Only I am getting poor results in terms of data latency when I am going to compare with the direct data transmission and leech protocol. However, I am getting better data latency performance in comparison to conventional wireless sensor network, and you can see that in terms of network lifetime I am getting in all aspects I am getting better results. The left column is indicating simulated IoT test bed and right column is indicating real field sensor node deployment. This is another research work what I have done. This is during my postdoctoral research I have done, and I have told you that you can use this wired links, you can use heterogeneous sensor node, you can use data mule mobile nodes, you can use to create the long range links, and the last and at best method is beamforming. Beamforming is an approach through which you can do the directional beamforming, and if you are doing directional beamforming, whatever the energy you were wasting to transmit the data in omnidirectional, you are saving that data, and in a direction you are transmitting the long over the long distance. And
But for beamforming there should be multiple antennas and you have to do lot of signal processing.
that is the reason, yeah, that is the reason. Next, right now I am working on this particular research problem, that is collaborative beamforming, so that I can reduce the hardware complexity and the cost of the network, and we are going to submit this paper very soon. This is collaborative beamforming, where individual antenna is mounted with single radios, and we are treating all the sensor nodes and we are grouping it to perform the collaborative beamforming, so that we can reduce. So what you have told me, that is already I have worked and we got good results, and that is going to be submitted soon.
For that we make a cluster.
We make a clusters, and the more critical problem will be that which set of nodes you should take in the within the cluster, how many set of nodes we should take within the cluster, and in which direction we should do the beamforming. And that was very like hectic for me. It took almost more than 1 year to identify, but we are successfully able to do. Okay, so this is LCMB beamforming. So okay, so you refer this my research paper, you will come and you will understand. So this is the detection and estimation performance. This is not my paper, this is not the result of my paper. I got motivated from these papers, and small word is giving better result. This is another work I have published in IEEE Transactions on Cognitive Communication in Networking, and right now I am working in this machine learning models to introduce this small word phenomena. Right now I have used this reinforcement learning mechanism to transfer the data over the network. Leave it. So this is the time varying scenario. This is I got minor revision on this particular paper, IEEE Transactions on Network and Service Management. So I have to conclude it quickly, so I am skipping some of the slides, sorry for that. So this is time varying scenario. In previous static scenario was there, and this is on 5G mobile network scenario. We have done the beamforming. This paper is already published in IEEE Transactions, and this is UAV assisted small word LoRa communication we have done. This is published in IEEE Internet of Things journal, and there we have introduced a small word phenomena within the layer of UAVs. That was more critical problem because the network was dynamic and it was very fast to identify that which node pair I should select at time instant t1 to introduce the long range link. That was very critical, but we have addressed and we got good results. and the last one is UV based optical wireless communication solutions, what in the first I told you. And right now I am working with Professor Murat, Turkey, on this particular problem, and we together we are able to address this multi-layer UAV assisted network, and we are doing optical. The main challenge is when you are going to, like, conventional wireless network and optical wireless communication, difference is like when you are modeling the wireless communication, that is more complex in case of optical, because the turbulence and other issues also you have to take into the consideration, but we are able to address the problem successfully. So thank you. Sorry. So I have skipped some of the slides, so sorry for that.
Sir, you have used NI sensor node. Tell me which sensor node you have used.
3230, you just type NI 3230, but right now if you will ask NI, they have not providing, that is obsolete, that is gone. Now you, if you are trying to real field sensor node deployment, you have to use some other.
And which LabVIEW software, which toolbox you have used for
So LabVIEW, when you will open directly, it will be a package, a complete package they will provide it. No, it will not, you will not be able to see here, because that is directly they will provide you the package, whole package. On that particular package you have to see the data.
It is not
conventionally you will not be able to see. When they will provide you, when you will connect them directly, it will be on that particular platform you will be able to see.